Thermal energy storage is one of the hot technologies of the energy transition. In today's video, we're going to see a take on this from MGA Thermal, who I visited a few months ago when I was in Newcastle, and I got a tour of their new pilot facility that they're in the process of putting together. I found out about the technology, the manufacturing process, and applications and their scale-up plans. I'm Rosie Barnes. Welcome to Engineering with Rosie. So yeah, thermal energy storage is a bit of a hot topic these days. You can store heat energy in a huge range of materials, from water to gravel and a lot of things in between. New versions of this tech pop up in the media pretty regularly. For example, there's been a Finnish sand battery getting a lot of attention recently. And on this channel, I've covered thermal energy storage company Steesdale, who are using gravel to store heat, and seasonal thermal energy storage projects in Canada and Scandinavia that simply use large pits of water. Basically, any material that you can heat up can be used for thermal energy storage. But ideally, it will be a cheap and abundant material that can store a lot of heat in a small space without causing too many problems as the material is heated and cooled repeatedly. The topic of today's video is an Australian startup company called MGA Thermal, who have a new material that they're using to store thermal energy that ticks a lot of the pros and not that many of the cons that I just mentioned. The MGA stands for Miscibility Gap Alloy, and that's their key innovation that came out of research from the University of Newcastle about 10 years ago. Since then, they've been working on the commercialization of that innovation, and now they're just about to start ramping up production. Their product is a solid brick with metal alloy distributed throughout in such a way as the metal alloy becomes molten, but the brick itself stays solid. So it's supposed to be kind of the best of both worlds between a molten metal that can hold a lot of thermal energy in a small space and a solid brick that's easily contained and doesn't cause a lot of problems with thermal expansion. I visited MGA's pilot manufacturing facility a few months ago and got a tour from Arden Jarrett, their business development manager. And then I spoke to their co-founder and CTO, Alex Post, separately online since he wasn't available the day that I was in Newcastle, unfortunately. So first, let's ask Arden to show us MGA's thermal bricks and tell us what the miscibility gap alloy is and how it works.
We make these blocks and they're called miscibility gap alloy, which essentially means that there's two materials that'll never mix. It's like oil and water. No matter how much you shake them up, they're not going to mix up. The two materials are graphite and a metal alloy. We describe it like a chocolate chip muffin. If you heat up a chocolate chip muffin, the cake stays solid while the chocolate goes through a phase change and it melts while you heat it up. So our blocks are pretty much the same in that the graphite is a matrix which holds the aluminium alloy particles in place, and while that's melting, the particles go through a phase change and it stores more energy through a thing called latent heat.
So all those light spots, that's an aluminium alloy, and that's what's going to melt. And this matrix is some graphite, that's the cake, and then the aluminium is the chocolate chips.
There is a special ingredient in there.
I assume you're not gonna reveal it. How does the technology work and what makes it different from other thermal energy storage?
Our core invention is a composite material which is designed to store thermal energy. There are a lot of different thermal energy storage alternatives on the market which are generally based around repurposing existing materials like graphite, concrete, silica, existing material properties. Whereas we've gone back to first principles and said, what are the criteria that make a good material for thermal energy storage? Let's try and design a material that fills that purpose, and that's the heart of our technology.
And so what are those criteria then?
So safety, capacity, cost effectiveness, and sustainability. Safety is a big one. You have to look at events where you have a rupture of the thermal energy storage material, where it's exposed to atmosphere energy density. You have to be able to contain a lot of energy in a very small space, which intrinsically is hard to do safely because fuel can combust. We've seen batteries igniting. It's just hard to store a lot of energy in a small volume by definition.
How does it work?
You have material changing from one form into another. You have a solid turning into a liquid. There's actually quite a lot of energy associated with that transition. It takes a lot of energy to melt something. When it freezes, you can get that energy back. So it's a good way of storing a lot of energy. The trouble with that is it's very hard to use that energy and to handle that material in a safe way. That means you've got to handle something when it's solid, but also when it's liquid. So it's hard to design infrastructure to contain that. In our case, we're looking at liquid metal. Liquid aluminium specifically will eat into almost any material that you want to contain it in. It's very hard to contain liquid aluminium. You have to be very, very careful with it. From a safety perspective, liquid metal at 700 degrees is obviously quite dangerous. And you also have to cope with quite a big volume change, the same as water freezing into ice. There's a big change in volume associated with that phase change, which means if you make a vessel to contain your liquid aluminium, when it freezes, it could crack that container because of differential thermal expansion, because of a volume change with that phase change. So we've tried to address all of those issues by making a composite, a solid block of graphite, and within that block we have small particles of aluminium, so individual grains which are completely isolated from one another, contained within this graphite block. And that means that from a large scale perspective, it's always just a solid block because those grains are all completely enclosed. But from the perspective of energy storage capacity, you're still melting that aluminium and storing all that energy. You just don't have to worry about all of the difficulties of handling it.
So then you've got these blocks. What are you going to do with them?
So there are a host of different ways that you could use technology like this. Waste process heat, heat pumps, or direct electric heating through resistive heaters. The initial market that we're targeting is electric input. So yeah, we use electricity to power resistive heaters, which heat up our blocks. There is a lot of electricity available, which is very, very variable. The market that we're trying to target is to firm up that variable input from the grid or from a behind-the-meter solar farm to heat up our blocks electrically, and then to use that to provide a firmed supply of either process heat for an industry or electricity to dispatch back onto the grid. So it's electric heating of our blocks. We heat them up to about 750 degrees when they're fully charged. So all of that aluminium that's contained in our blocks is fully liquid at that stage. It melts down at 660. Then we use that to heat up a flow of inert gas, which circulates across our bricks in an enclosed insulated container, and then can be delivered to any process that we want downstream.
And you said it was, the duration was 10 hours, is that right?
Yeah, that's right. So we can store for longer than that, but the pilot that we're performing at the moment is designed to provide 0.5 megawatt of steam for a continuous 10-hour period.
And can you just tell me what are some example applications that would need that kind of steam?
You know, there are a whole bunch of industrial processes that require steam, though, like paper manufacturing, dairy, and quite often at the moment, the energy source for that steam is a gas-fired boiler. So obviously, you know, people are trying to replace that to decarbonise, but they don't have a firm supply of that steam. You know, installing solar farms to power an electric boiler and that kind of thing, but they can't run that when there's no sunlight. So they have to shut down their entire process at the moment.
And how would you increase the power and the duration?
So to increase either the power or the duration, we just add more bricks, which means a larger insulated enclosure as well. Each of our bricks can store a kilowatt hour of thermal energy. In terms of dispatching heat, which is what we're demonstrating with this pilot, we're very, very efficient. First of all, we have the electric charging part of our process. In most electrical processes, heat is your form of losses. So electric heating is extremely efficient because your only loss mechanism is heat, which is what you're using. We're in the order of 98% efficient for our charging. We can store it. We lose about 2% per day of our stored capacity just as thermal losses from the container. And then discharging, we're also very efficient because we run a gas loop for this steam generation. Gas comes out of our storage, it goes through a heat exchanger which creates steam, and any heat that is left in that gas after it goes through that heat exchanger, which isn't transferred into steam, then goes back into our storage in a closed loop. So round trip for heat, we're well above 90% efficiency. And converting to electricity is a little bit harder for thermal storage because you have to run a heat engine. So for anyone listening who has a background in thermodynamics, they'd be aware that heat engines have something called the Carnot efficiency associated with them, which means you actually have limitations on efficiency dictated by the laws of physics, where you can't convert heat into electricity at 100%. A typical steam power cycle is in the order of 30%, maybe 40% efficient at the very large scale for a power station, which basically dictates our round-trip efficiency if we're producing electricity.
So round-trip efficiency to go from electricity to electricity is going to be in the 30%. Is that expectation?
In the 30 to 40% range. Yeah,
okay. So that's obviously like a lot lower than a lithium-ion battery or pumped hydro or most kinds of energy storage that people are looking at. So what makes your technology attractive then? Like when would you use it?
Round-trip efficiency isn't actually your key concern. If you have more energy than you know what to do with in the middle of the day, then as long as you can capture any of that to use when you need energy, as long as you can do that cost effectively, then it's worth doing. So what we're really trying to emphasize is that even though the round-trip efficiency is much lower than batteries, the total cost per joule of energy that you pay for that firm's renewable energy out of the back of the storage is still lower than batteries. And that's because the capital cost of our storage equipment is so low. So you're getting very, very cheap energy. You're storing it cheaply. You store the 30% that you can effectively recover, and then you discharge that.
One of our potential applications is repurposing thermal power stations into renewable energy storage facilities. So that means repurposing the turbine and the grid connectivity and the building itself, taking out the boiler and anything to do with the coal, putting in a TES unit with our bricks, and reusing the infrastructure to capture the electricity out on the other side. So because it's designed to be bulk energy storage, so the efficiency comes when it's a really large system. A lot of our most interested customers are solar PV farms because they're spec'd their output for 9 a.m. during the day. So it's peak load shifting, essentially. So if you collect a large amount of electricity during the day and then use that large amount at night.
Okay, as electricity though. And they're happy to lose more than half of it.
Because they wouldn't have been able to use it anyway.
When you say it's going to be, much cheaper than batteries, is it that based on how much it costs you to make a brick today, or you've got some assumptions for the future about how costs are going to come down?
Yes, that's based on the costs of our current manufacturing capacity. We can make very, very large quantities of our bricks quite economically. And because we're using readily available raw materials, we don't have lithium, we don't have expensive materials in our bricks. Everything that they're made out of actually is in the top 25 most abundant materials on the Earth's crust.
What about recyclability? How long would a brick last for? And then what do you do with it at the end of the lifetime?
So we're targeting a usable lifetime for these bricks for 30 years. In reality, we haven't managed to break them yet. We haven't tested them to 30 years yet, but that is our target for the lifetime of the bricks. At the end of that lifetime, then, we can actually recover the raw materials that make up the bricks and recycle them back into new bricks. The two components that we make them out of are very, very happy to exist purely in isolation of each other. So when we crush them up and separate them into those raw materials, then we can essentially recycle them, and it's like new feedstocks.
Is how small can you make it? Because every time people see something large-scale energy storage, they're like, oh, I want one of these in my house.
Okay, so there is a difficulty with having a thermal energy storage for household use, especially if it's for electricity. That's because you need this power cycle to convert the heat into electricity. That is a technology that doesn't yet exist at the household level, which means if we are to develop a household level product, it'll have to be for heat only. So that's our initial target. As crazy as it is, the need is there at the utility scale for technology. So we're targeting 100 megawatt plus sized installations of thermal storage.
Your forward plans, like what scale are you going to reach and when?
We're essentially scaling up tenfold every 12 to 18 months. So this is going to make over 1,000 bricks per day. And so the next scale up in the 18 months after that is looking at 10,000 bricks per day. And then 100,000 a year after that. Right. Things are scaling really quickly. We've got 20 gigawatt hours of interest in the pipeline, and we're scaling in order to meet that demand.
So thank you for that tour. I need to give a big thanks to MGA Thermal for allowing me inside to see all their equipment and how their pilot line is coming together, plus some of their research facilities, and explaining how this all works. One of the interesting things about this technology is the scale. It's quite cheap, the materials involved, and so you can imagine that you can make many, many, many megawatt hours or gigawatt hours potentially of energy storage in this way. You can use recycled materials and you can recycle it again at the end, and hopefully, according to them, at least this is going to be a cheaper way to get this real bulk energy storage. Their scale-up plans are quite aggressive, and they've got quite a lot of projects in the pipeline. So I think this is going to be a really interesting one to watch over the next few years and see how it plays out, see how the costs of all the competing technology end up going, to see what kind of contribution technology like MGA can make within the broader context of energy storage and renewable electricity system in general. Thanks a lot to MGA for the tour. And as always, big thank you to the Engineering with Rosie Patreon team. If you'd like to join us, there's a link in the description. And thanks to you all for watching. I'll see you in the next video.